Thanks. I'll begin with a word of prayer again. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Pray you'd help us to just go over some of the salient features on test 3, Lord. In your name I pray. Amen. Okay, so I think I will show you the ones I have solved. How about that? So, problem number 1, particle of mass m, energy, this potential energy U of x equals to, was that 10 times x squared minus x to the 4th, right? And so you're supposed to make a potential energy slash velocity position graph and plot several energy levels and analyze these different motions, okay? So here's what I come up with. So here's what I got. Let me find my laser. Where's my laser?
Laser got the students?
Yes, I am great.
Laser ID.
Okay. Don't tell your mom. All right. So this is the potential energy graph. I used Desmos to make this. And here's E equals minus 2, minus 1, 1, 2, 3. And I put the critical energy here in gray. It's kind of hard to see. So the rule, of course, is that kinetic energy has to be positive. So that means certain motions are forbidden. For example, you can't have energy 1 and be between here and here, right? That would correspond to negative kinetic energy, which is classically forbidden. Likewise there. So then you track down here in the velocity position plane, and these are the energy level curves that you get. And so I don't think I really asked this question of you clearly, but you know, it would have been a better question, slightly better, is if I'd ask you to classify the critical points. I don't think I did that though. But we haven't.
need a bathroom.
You need a bathroom.
Yeah.
Well, that's interesting. All right. Well, you'll take them. Pause. I'll be right back. Sorry about that. Here, let me, I'll come back to that one. I'll let you look at this one in my absence. How about that? All right. Come on, guys. Guys, hurry. Isaac, you stay here. Unless you gotta go potty. You gotta go potty? Isaac, you gotta go potty? No? Okay. Well, stay here. Entertain the students.
Yeah, no, we fixed it. You know, I spent a long time fixing that. I'm being really irritated about it.
Like, you don't understand, that's all she did the rest
Like,
of
I was so irritated.
the entire, like, for like 2 hours, I think.
I justified my answer though. Like I had a reason as to like in my B through B they're relying on that graph. And so I had to make up things.
We're back. I should have known after his third refill of root beer that this was an inevitability. If I'd been smarter, I would have done that before we started. Okay, so going back. What, Matt? What? You want to sit there? All right. Careful. So, where's my laser gone to?
Oh no! It's a laser for students!
Huh?
You're planning to kill the students! You're trying to kill the students, aren't you?
I'm trying to kill the students. No, that's not the final yet.
Yes, you are. You are trying to kill the students!
It's too soon?
Student killer!
Huh. Well,
You blood all over your pants!
that's weird. Oh, there it is. Who knows why I put it there? All right, so these are different energy levels. So I ask you some particular questions about like energy 1, which is the blue one. So I say, what if you start at like, 0.3? So if you start at 0.3, that means you're either here or there on this energy level curve, which means you're either going like that or you're going like that. And so anyway, whatever you do, you're always going between this and this maximum position, right? So the motion's bounded in that case. On the other hand, if you have energy 1 and you start out over here, you're either just going to go off to infinity like that, or you're going to bounce here and then go off to infinity. So either case, your motion's unbounded in the other case. Energy level 3, it doesn't matter where you start. It doesn't matter where you start. There's nothing to stop you, right? So if you look at energy, if you look at energy level 3, there's no place where the energy level intersects the potential energy, right? And that would be a place where it has velocity 0, right? So the velocity is always non-zero. So if you start out moving to the right, you keep moving to the right. If you start out moving to the left, you keep moving to the left. And so the motion's unbounded in that case D. Any questions about this? So if I had one on the final that was like a little bit less graphically intense, say like u of x equals to 2x squared or something, do you think you could do that problem? Maybe? Okay. No fighting on the chair. Come on, guys. All right, everybody down. Everybody down. Everybody down. Everybody down. No, nobody's sitting down. No. Here. Go. Go on. Here, Matt, you can have. Where'd the cap go? Here.
What are you doing?
Have fun. There you go. Okay, so Coach, you have another problem. Any questions about this? I mean, for part B, you could ask why. That would be a reasonable question. But basically, we just plug in the solution x equals to the r, y equals x to the r. That gives us the characteristic equation r times r minus 1 minus r plus 1 in here, which factors into r plus 1 squared. So r minus 1 squared. Open? What are you going to do? All right, there you go. It's open. And then as we derived in class, if we got a repeated root, we end up multiplying by log x, right? It's kind of surprising, but that's what it was. On the other hand, down here we had minus 4 plus or minus root 17 over 2, so we kind of this ugly looking functions. These are x plus 1s. I'm sorry, it got squished. I forgot to write x plus 1, and I changed my x to an x plus 1. It wasn't pretty. Sorry about that. But obviously, x plus 1 plays the role of x here, right? I mean, I guess technically I should make a substitution of... You drink all of it? What? Ah, you drank all of it. One of his favorite things to do is to drink my coffee. So if I have like a sip left, I
You want to see my blankie?
I don't have coffee.
You have a blankie?
A blankie?
A
No.
blanket.
A blanket? I do not have a
Yeah.
blanket either.
No.
My wife warned me that if I brought all three, their boyness would be amplified. It was foretold. But in isolation, they're less. What? Oh, we'll make another one. So here, we have minus. Matthew, here. So here we have a complex power, and so that requires a little bit of special attention. The minus 1 gives me 1 over x. The 2i gives me cosine 2 log x and sine 2 log x with the I. I pick off the real and imaginary parts of this to give me the real solution, as we discussed in class for something similar. Any questions? Okay. Yeah, so this problem was a little bit unpleasant, but I hope that it was fairly clear what to do here. You want to convert everything to power series in sight, plug in a power series for y, a power series for y prime, a power series for y prime prime, and then we just collect terms. So if I look at constant, I've only got this 2c2 here, and there's no constant terms from this guy, right? Over here I've got 1, just a soda wrapper, 1 times, what did you do? It's okay, Matthew. Hey, why don't you guys use a different board? Isaac, you use that board. Matthew, use this board, okay? Here you go. You can even use this desk. All right? There you go. So, getting back to the story. Constant terms give us this, so we get a relation between C2 and C0, like so. Linear terms, you've got this 6C3. There is no linear term in here, right? Because we have at least x squared in every single term if you multiply. And over here, I've got 1 times x, which gives me a C1. And that's it. So that gives me this and that. Actually, right there, I could have stopped, because that already gets me to third order, right?
Have anyone seen other markers?
Other markers? You mean like this one? Okay, there you go. So I did more, but I didn't actually use these for my answer because I didn't need them, right? So here's up to third order, the answer. Yeah, it's better. No, they're laughing at Daniel. That's right, Daniel, they're laughing at you. That's not a walkie-talkie, it's my mic. Leave it alone. What? What do you want? Open it. Oh, okay. This is why you shouldn't try to lecture with children. Now here I made a grave mistake. I forgot to make my formula make sense for 0, which means I could include the 1, right? So if I'd been smarter, I would have rewritten this formula so that I went all the way to like 3n plus 3, you know, and 3n plus 2. And then I could have put n equals 0 to infinity, and I could have lumped the constant function into this lovely formula. And likewise down here, x, I could have lumped into here if I had been more forward thinking with my formula. I see that. What is that? A mountain. Oh, okay. Very interesting. A question? Yes.
On a problem like problem 3, how you solved the end for things in terms of C0 and C1. For full credit, are you looking at things in purely terms of C0 and C1, or if I choose 2 other constants, is that okay as well?
No, you really should. For full credit, you do want to write things in terms of the lowest coefficient. Yeah.
Okay.
Otherwise, you're not. I mean, it's not incorrect, but it's just not done. Generically speaking, we should only have 2 arbitrary constants in the solution. Now, if you wanted to be weird you could solve, I could put everything in terms of C2, right? Like I could even put C naught in terms of C2. So I could use C2 as my coefficient, but it'd be weird. Yeah.
Well, I solved everything in terms of C naught. There's a way to solve for C1 in terms of C naught.
No. I don't think so.
I think we usually execute.
I don't.
Eraser.
Oh, well, just don't get it on there anymore, okay? You'll be fine. It's not ruined. Go play.
Erasing the color.
It's not erasing the color. You're fine. Go color. I probably what happened is you missed a term and then it introduced a coupling that wasn't actually there. That'd be my guess, but that shouldn't happen. Because like generically speaking, the theory still holds that there are two linearly independent solutions. So they gotta be there somewhere. And symptomatically what that means is that a few of the coefficients could be 0, but there always has to be some sort of like, well, there doesn't, the linking between coefficients can be much uglier than we typically, like this is still reasonably nice. Let me show you something that's not nice.
This is not nice.
Ow, that was unnecessary. Yeah, number 5, exactly. Now, this part of number 5 wasn't bad.
This is number 6.
Oh, number 5, oh yeah, oh well, so. Yeah, I don't have that one written out. But, sorry about that. I had things to do this weekend. It's a long story. Don't even get me started. So I do hope to provide you, I mean, I'm just not done with my solution yet, is what I'm telling you. So like 5, I will write the solution up and post for you guys, as well as the ones that I don't have written yet is my plan. What happened to the mountain? What's that now? Is that fish? Is it explosion? Okay. So you guys are fine with this one then. This one did not haunt your dreams. This one was
It was okay.
it was okay? So this part of it wasn't bad, right?
No, that was fine.
That one, I mean, so it's square root of 5 to the 2 plus I, square root of 5 to the minus 2I from the center point. So it's only 2 to 3. So 3 is the closest singularity. So that tells me the open interval of convergence because it's the closest singular point. This was unpleasant a little bit, right? Because I had to take this, I have to rewrite it in terms of x minus 1 expansions, right? Maybe you guys didn't do this, but you do need to do that because we're centering it at 1, so that means I have to expand in x minus 1. So this is not in the right form yet. To put it in the right form, I can use Taylor's theorem, which expands x squared plus 4 is 5 plus 2 times x minus 1 plus x minus 1 squared. So I get these 3 terms from that. And then this is geometric, just in disguise. So I shift it to look at minus 2 plus x minus 1. I factor out the minus 1/2. That's geometric series. There's the first 3 terms. I don't probably even need all of them. And then at this point, I've got everything in the kind of format that I need in terms of like expansions of x plus 1, excuse me, x minus 1. And then, what's that?
Oh, I was super wrong.
Yeah, I'm guessing you have a lot of company. Yeah, yeah. Show of hands, who did this one wrong? There we go, yeah. Okay. So that's why I brought the pizza today. So, yeah. Make you feel better. Let's see here. And also, again, the final. Sorry about the final. So, yeah, the final, I mean. Like Nehemiah told me he hadn't been challenged yet this semester, and I was like, okay, let's see here. I will provide a challenge on the final. Don't worry. Finally, something interesting, something original, something new, something to build algebra skill that you didn't know you had yet. All of these things.
We haven't had a ninja problem or like a Ron Swanson problem.
You want a ninja problem or a ninja? You want a ninja and a Ron Swanson problem on the final? Challenge accepted. It may not be an interesting one, but anyway. So this one is what I was talking about. These recurrence relations are really quite ugly. Look, it's got a 0, a 1, a 2, a 3, a 2, a 1, a 4. Like it's all connected. And the reason for that is that the solutions to this are neither even nor odd. They've got some kind of intertwanglement, to use the technical term. And so like A naught, of course it picks up the constant term, right? And it also picks up, you know, let's see here. Where's my stupid equation gone to? It also picks up, of course, aw, man. No, I'm fine, I'm fine. So I pick up the constant term and then this minus 1/10 right here. But the A3, dang it, I keep losing track of where I'm going. On the other hand, when I look at A1, oh man. I mean, this term is immediate. Where did I get this from? Do you guys see it? I think I've done something in my head and not written it down.
Left of your boxed answer, there's A1 minus A1 over 4. Oh, never mind. I didn't realize it was.
Okay, so this right here says that let me write out what this means, and maybe that will explain it to you guys. So I've found A2 equals to, what is it, 1/10. Stop that, Daniel. A2, A1 over 2? Minus A naught, yeah. So in the solution, we have, you know, A naught plus A1 times x minus 1 plus A2 times x minus 2 quantity squared, right? Plus stuff. Good grief, x minus 1 quantity squared. So if this is, I may have an arithmetic mistake here still. So that's A1 over 20 minus A naught, right? It's x minus 1 squared. Just this piece, right? What is that? Dinosaur roar, okay. Noted. So my point is, when we rewrite this expression in terms of just factoring out the A naught, of course we get the 1 that was here, right? But we also pick up from over here minus x minus 1 squared, right? Of course there's, and then whatever else happens. And then for, let's see, for A1, I get my x minus 1, right? But what else do I pick up from the A equals 2? From this term, I pick up what? I pick up plus 1/20th, right? X minus 1 squared. And you see the danger of trying to do that in your head because my answer is wrong, right? In its current form. So here's the solution up to quadratic order right here. See how I did that? Next time I can leave you home, Daniel. Let's see here. No. Okay, so. He doesn't have. I wasn't too worried. He doesn't have a lot of experience throwing soda bottles. So, this. So this is wrong, right? Because that 1/5 should be a what? It's 1/20th. Does this make sense how I did this? All I'm doing is I'm just collecting together the solution I said and facing the consequences of, you know, what it means to plug it in and look at it power by power. It's just this one is kind of nasty because, as you can see, at least the solution which is paired with A1, it's not just sum of odd powers or even powers or some kind of nice thing. It looks like it's going, Daniel, power by power. Stop it. And I think I know what the 1/5 was. I tricked myself into thinking I had 2 over 10 versus, 2 times 10, right? No excuse, but I need to fix that, obviously, right? So let's see, the problems that I haven't talked about yet are what? 5. Frobenius solution, eh? So did you guys generally reach a consensus on this one? I mean, here you go. I'm going to take that one back. You can keep this one. Anyway, I will try to write up a solution for that. I would try to do it on the fly right now, but I don't think it would go well. Yeah. I mean, you could watch me, but it would just be punishment for both of us. How about number 7 and number 8 and 9? Did these go well? Were the examples I did in class somewhat representative of them? Yeah. So I hope to write up solutions for these and post them for you guys. I'm sorry I don't have them ready right now, but I do think it's much like what we already did in class. Like for example, this one, I can tell you from looking at it, it's going to be a sum of sines, right? And then that's actually going to require Fourier analysis. Sorry about that, but you know, it's going to happen sometimes, right? You actually had to find the Fourier expansion of this to fit it, right? Yeah. This one here looks like, well, I don't know, I can't eyeball these things, but this, I don't think you had to do Fourier expansion here because you can convert that to like 1/2 of 1 minus cosine 2x. If the solution was in terms of cosines, then there wasn't really Fourier analysis in this directly, was there? Just trigonometry? Am I wrong? Did you actually have to do Fourier expansion here?
I think we did just because we didn't use that identity.
Oh, because you did the integration rather than doing the trigonometry?
Yeah.
That's funny. Okay, I mean, nothing wrong with that. Well, no, there's something wrong with it, but it's okay.
Wolfram alpha.
Oh, Wolfram alpha, okay.
Yeah, the internet has lots of good help.
Oh, you guys. Oh, you draw on your plate, huh? Why don't you show them? Don't show me. No? And this one was awful lot like the one we did in class, I think. So anyway, I will hopefully write solutions for these and have them posted for you sometime. Obviously, it's fairly clear. By the way, okay, so just to be clear, I will not ask you a Frobenius question on the final despite the pizza. All right? Cauchy-Euler, that's totally fair. I might ask you Cauchy-Euler. I mean, technically speaking, Cauchy-Euler problems are Frobenius problems. They're just really easy Frobenius problems, right? I mean, they're regular. In contrast, I certainly might ask you about the domain of convergence on the final, right? I certainly might ask you to find the first couple terms in a power series solution or the complete power series solution. Like number, what was that? Where'd that go? We didn't talk about this one yet, did we? I somehow skipped past this. So something like this possibly could be on the final. You know, there's plenty of ones that are a little bit easier for me to grade than this one, you know. And let's see what else. There's parts of the partial differential equations that I could test on without testing the whole thing. You know, like I could say, here's the boundary value problem. Find the k for which there are solutions and describe the solutions. So like that's just one part of the process that you went through. So I might test on a subpart, or maybe just here, I'll take it from you. Thank you. You don't need to go in there. You're fine. No, you cannot take your shoes and socks off. Let's see. Can I take my shoes and socks off? What? That goes for you guys too. None of that. Travis? Oh, sorry. Travis looking at his feet. But if you want to take your shoes and socks off, you can go to Dr. Sprano's office. That's where this sort of thing is allowed. Here. Yeah.
You deserve it.
Ow! All right, so, my back. Okay, so on the final, we also had another 2 tests, yes? And so there's the first order stuff, which you should remember and go back through. There is constant coefficients, annihilator method, all of that, variation of parameters. I would only test n equals to 2 on the final. Like higher order variation of parameters is not fair game. Of course, you need to know how to solve systems with eigenvectors and the magic solution, magic formula. Yeah, Laplace transforms. So you are allowed to, you should in fact bring your Laplace transform sheet, and then you're also allowed to put it whatever you want on the back of that in addition, you know, or in between the Laplace transforms if you like. If you'd rather take the Laplace transform sheet and take another sheet that you have and staple them back to back, that's also fine with me. The point is that you can have two normal sized pieces of paper front and back to look at. I don't care how they're assembled if they're, again, two separate physical sheets stapled together. That'd be fine.
So we're allowed one front and back, or 2 sheets of paper front and back?
You're allowed the surface area of one sheet front and back, but you could take 2 physical sheets and staple them back to back. The point being that the part which was stapled together you couldn't look at anymore. See what I'm saying?
I mean, it depends on how well you staple it, I suppose.
I reserve the right to put a piece of gum between your pages if I need to.
Do you think we're going to need to find Fourier series?
No, I don't think Fourier series is appropriate for the final. No. What? Higher what?
Matthew, what did you say?
You need your plate?
Oh, you threw your plate. Okay. Say thank you. Other questions? Yeah.
Well, going through test 1 and test 2, would be a good representation of what we should study for our final.
I think they'd be helpful, but as usual, I will tell you the homework is really what's more representative. And so for here, I guess that means the recommended homework, right? The quizzes. Of course, modulo my comments, like I just said, I wouldn't do Fourier series. Wouldn't do the full Frobenius thing, or even the, well, like I said, except for the Cauchy-Euler. Let's see here. Whoa. Nice job. Let's see here. Other questions?
Guys, do you think this picture is cool?
Yes.
It's cool. If you gotta jump a giant ball like that high. Hey, back guy, I'm back guy. Guys, wake up.
I don't know. So other questions? Daniel, stop it. I think I brought one boy too many. Let's see here. You can guess which one. Yeah.
I haven't checked in the last day or two, but as of a couple days ago, the lectures on wave and Laplace equations were not uploaded, if I remember right.
Is that right?
Are those going to be
Yeah,
up?
I don't think the link for your lecture notes is
Whoa.
The link for the lecture notes, like through Blackboard, goes through like Laplace equations and stuff, but on your super math one, it doesn't.
Well, we're talking about,
Yeah, I was talking about
It's a rope.
his lecture.
It's a rope.
so here's the YouTube. Are we talking about YouTube
Yeah, I was
lectures?
asking about you.
He's talking about YouTube.
It went through heat equations, I believe.
Not Laplace transform, Laplace equation from
Like the last two lectures?
Don't- This one?
No, I mean wave and Laplace equations. Like,
Oh, you mean from like last week? I didn't.
yeah.
Oh, so I'm missing a day in here somewhere, huh?
There's after 418. It's just
I'm not sure.
Huh. So 425 are we missing maybe? 425 and 420. Yeah. Okay. I'll have to look at that then. See if I can find them. That's weird.
They're in your notes.
Yeah. Huh. Strange.
Guys, look in the hole there. Look at that hole. Look at that hole. You're gonna see a
I'm sure you have something more productive to do. If you'd like another piece of pizza, welcome to help yourself. Still have some more smokehouse up here. And nope. Pepperoni.